So now that we've talked about the names of the polar graphs, what we're going to do now is actually graph them using our graphing calculator. Now we talked about symmetry the other day, how sine graphs are symmetric to the y-axis or pi over 2. And that was the y-axis. And how the cosine graphs are symmetric to the polar axis, which was the x-axis. So just a quick note, we got to make sure our calculator is in the correct setting, so let's go and verify that. So for our mode, we want to be in radians and we want to be in polar. And we talked about sequential or simultaneous. It doesn't matter for what we're doing today, so we'll just leave it in sequential. And then press second and zoom, and we want to change this to polar GC. Right now, and then we go to window, make sure 0 and 2 pi, okay, and then our theta step 0.1, and then -4, +4, and there might be some problems where we need to change this. If we get an error when we graph this or try to trace a point, then we'll need to fix that and change our window. All right, now we're going to sketch the polar graph and then name the shape. For circles, we're going to use our table values of 0, pi over 4, pi over 2, and 3 pi over 4. Because remember, we talked the other day that we have repetitive points when it comes to circles, and we still need 4 points to get an idea of how the shape should go. Right, so this is a circle because it's in the form r equals a sine theta, like we don't have anything being added or subtracted. We don't have a number in front of theta, so this is a circle. So when we graph this, y equals, so then we're going to do 4 sine theta, close parentheses. And there is our graph. So now to get our values for r, because remember we're going to use 0, pi over 4, pi over 2, and 3 pi over 4. We're going to press the trace button on our calculator, and we type in, see when we type in 0, r is 0. When we type in pi over 4, so second, the exponent key pi over 4, we get an r value of 2.82, or 2.8. So let's see, we have 0, 2.8. Then we're going to have to do pi over 2. We get an r value of 4, and then 3 pi over 4 gives us an r value of 2.8 as well. For 2.8. So let's go ahead and plot the points. We had 0, 0, and then pi over 4 we had 2.8, so 1, 2, and a little bit, 2.8. At pi over 2 it was 4, so 1, 2, 3, 4. And at 3 pi over 4 it was 2.8, so 1, 2, and a little bit right there. We know it's a circle, so let's make sure we draw it a circle and not a square or a diamond or anything like that. So that is as much as we will need to do for these graphs. Identify it, substitute it into the calculator, and then plot those points. Right, so then the next one, r equals 2 cosine of theta. This is still a circle. So that means our theta values, 0, pi over 4, pi over 2, and then 3 pi over 4. And again, if you forget how to do the calculator, you can always just substitute these values in for theta. Like for example, 0 2 times the cosine of 0. We know the cosine of 0 is 1, so 2 times 1 is 2. And you could go all the way down with those if you wanted to, and in some instances it might be even a little bit faster to do it by hand. All right, so we got 2 cosine theta. We'll graph that. So now can we press trace? When theta is 0, r is 2. So then we'll do pi over 4, and we get 1.4. Now pi over 2, we know the cosine of pi over 2 is 0, and 2 times 0 will give us 0, but we can still verify that. So pi over 2, we get an r value of 0, and then 3 pi over 4, we get negative 1.4. So we get 0, and then negative 1.4. So let's go and plot this now. 0 degrees, we go out to 1, 2. At pi over 4, we go out 1.4 units, so 1 and about a half. When theta was pi over 2, so going this way up towards there, we're at 0 units. And at 3 pi over 4, we got a negative r value, so instead of going out this way 1.4, we're going to go backwards 1.4. So be right there, and this is what our circle would look like. Now let's look at the next page. For shapes that are not circles, we want to use those theta values. Now if you use those theta values for circles, your graph will not look like a circle using these 4 values. But because we have pluses and minuses going on, then we can use these values. So we can rewrite it like this. Distribute this, and then we would get r equals 2 plus 2 cosine theta. Well, when we look at it in this form, the two numbers are the same. And remember, if the two numbers are the same, then it is a lemicon, or the cardioid that looks like a heart, because we have those relationships that we had talked about with a over b. So remember, these are in the form y equals a plus or minus b cosine or sine theta. And if a over b is less than 1, we got that lemicon with a loop. So I'm going to write loop. This is just for me to remember as we do these problems. If a over b is 1, then we have that cardioid. And then if a over b, if a over b is greater than 1 but less than 2, that was that dimpled lemicon. And then we know if it's bigger than 2, it's the convex one. So I'm not going to write that one down because I have the other 3 written down, and we'll be good to go. All right, so again, because the a and b values here are the same, when you divide them, they reduce down to 1. So this is a cardioid. And now we will graph this. And we could graph it once I distributed or before I distributed, and we should get the same answer regardless. Okay, so there's our graph. So if we're going to trace, when theta is 0, r is 4. When theta is pi over 2, we get an r value of 2. When r is equal, when theta is equal to pi, we get an r value of 0. and then 3 pi over 2 gives us an r value of 2 as well. So we had 2, 0, 2. So we'll go ahead and plot those. So it was 0, 4. So start at 0 and then go out for 1, 2, 3, 4. At pi over 2, the r value was 2, so 1, 2. At pi, the r value is at 0, and at 3 pi over 2, we're also at 4. Now, the reason why we need to identify the shape before graphing is because if you just connect these dots right here, okay, that isn't a shape we talked about. So we know that this is a cardioid, so it's going to come and connect here, curve, and make this nice sideways heart shape. And that will be our cardioid. Now again, I'm not looking for perfection, but since we know this is a cardioid, this should look like a heart when we draw it out. All right, so number 4, we have r equals 4 minus 3. Our a value is 4 and our b value is 3. 4 over 3 is greater than 1, but it is less than 2. So this is going to be a dimpled lemicon. Dimpled lemicon. So our theta values, 0, pi over 2, pi, and 3 pi over 2. So we'll go into our calculators and type in 4 minus 3 sine theta. Graph that. So it looks like we need to adjust our window because the graph is going this way and that it looks like it's going down, but we can't see that. So I'm going to adjust to -5 and +5 and -10 and +10. Okay, so that gives us a better idea. And if we wanted to, the y max we could have left at 4. And that, because that didn't really give us any new information. All right, so when theta is 0, r is 4. When theta is pi over 2, r is 1. And then when theta is pi, r is 4 again, and 3 pi over 2, the r value is 7. So we had 4, 1, 4, 7. All right, so let's plot these points. 0, 4, 1, 2, 3, 4. Pi over 2, comma, 1. Pi, comma, and 4, 1, 2, 3, 4. And then at 3 pi over 2, we go down 7. 1, 2, 3, 4, 5, 6, 7. So then when we connect the points, we're not going to go as curvy as the cardioid. And then down here, we curve a little bit. Careful not to draw it like a V. We do want it to be a bit curvy because we don't really have any linear parts of these. So that would be our dimpled lemicon. All right, now number 5, our a value is 3 and our b value is 4, and that is less than 1. So this is going to be a lemicon with an inner loop. With inner loop. Now remember that inner loop always goes through the pole, the 0, 0. So because it's not a circle, these are going to be our theta values. So let's graph this and see if we need to change our window. So 3 minus for cosine theta. And yeah, it looks like we're going to have to change our window a bit to get this area over here. So I'm going to change our x minimum maybe to -7, and then y minimum, we don't need to go that far anymore, so -4. Okay. All right, so we do need to go back and change the y because we can't see what that point is. So our y max, maybe we'll change that to 6 as well, just to be safe. All right, we can't see that one down there. So, whoops, we need to change our y minimum also to -6. All right, now we can see everything. So trace, when it's 0, we have -1. Pi over 2 gives us an R value of 3. Pi gives us a R value of 7. And, whoops, 3 pi over 2 gives us an R value of 3 as well. So -1, 3, 7, 3. So 0, instead of going towards 0 degrees, we're going to go 1 in the opposite direction. Then when it was pi over 2, the R value was 3, so 1, 2, 3. When the R value was pi, R was 7, so we go towards pi 7 units, 1, 2, 3, 4, 5, 6, 7. And then when R was 3 pi over 2, R was also 3. So when I draw this, remember the loop has got to go through the pole. So I maybe start here, and then it comes this way, making sure we're keeping a nice curve. And that would be our lemicon with an inner loop. All right, on the next page, I want you to try this one. Give me the name of it and graph it, plot it the points, and then once you're done, unpause it and see if we get the same thing. All right, so this is how our graph is going to look with all the values. It is a convex lemicon because a over b is greater than or equal to 2. And then our graph looks like that. Now, remember, your graph will look a little bit different than your calculator screen because your calculator screen is wider than it is tall. So don't think that, oh, my graph on paper doesn't look like the graph that I have in my calculator. I've done something wrong. No, that's not the case. So that's it for graphing. You just need to remember what values for theta you use for which graph. Basically, if it's not a circle, it's always your quadrantal angles. But if it is your circle, then it's just going to be multiples of pi over 4 in quadrants 1 and 2. All right, so thanks for watching. Make sure to like the video and subscribe.